Stephen, taking it away.
All right, great. So yeah, let me say first of all, thanks very much to Huiwen and all the organizers, not just for inviting me, but for running this summer school. Um, I went to an INT Lattice summer school when I was a grad student. It was a fantastic experience. So I'm sure you're all having a great time here, even if you're only here virtually. Um, so yeah, so what I'm going to start with today is sort of a hopefully a short live lecture, which is the last piece I had intended to record, which I'm calling "How to Talk to Phenomenologists." Let me just jump right in. And this is sort of something I wanted to make sure to fit in, because it's sort of an important piece of all this. If you're looking at theories beyond the standard model, it's sort of being able to translate. And what I mean by that is being able to talk to phenomenologists and experimentalists and sort of make contact with the lattice results that you're presenting. And this is not about sort of the details of the lattice results, right? So I'm assuming you've done everything properly, you've done your continuum extrapolation, your systematic error analysis, all the technical details are dealt with, you have numbers. This is about how to go talk to your phenomenologist friend down the hall and tell them what to do with the numbers or what they mean for the experiment, how they fit into their model, okay? And the point of this, and the reason I say this is about translation, is there's a lot of things. There's a small, oftentimes, language barrier between lattice experts and phenomenology experts. It can be difficult to translate certain things. There's certain things that are really common or kind of trivial on the phenomenology side that are really hard on the lattice side, and vice versa. And so a lot of sort of being able to present your results in a usable way is sort of knowing how to do that translation. Okay. And so I'm just going to highlight a few things that you should know in this regard. Oops. Okay. All right. I meant to write this, so I'm not sure why it's here already. Thought I'd erased this, but let's go ahead anyway. Okay. So the first thing I want to talk about is factorization. When we study theory on the lattice, we study, of course, the strong gauge theory in isolation, right? When we do lattice QCD, we study heavy flavor decay, something like that. There's no electroweak gauge bosons in the simulations. And this is very obvious to us, but it's not something that every phenomenologist necessarily knows if they're not familiar with lattice. And of course, you need electroweak physics as well as QCD in order to get these things to decay in the first place. So if you're kind of a novice coming at this from the analytic side, you might wonder how you can get away with not having the electroweak theory in your simulation if you're studying electroweak processes. And the sort of key idea that lets us do this is factorization. And factorization is simply the idea that this is the right thing to do. We can turn off electroweak gauge interactions. We model the strong part of the interaction in isolation as a purely strong matrix element. And we can factorize the total amplitude into that matrix element times perturbation theory and kinematic terms. Okay. So one of the sort of classic simple examples of this is the heavy flavor decay here. So say D plus to L plus nu. Microscopically, this is mediated by a W boson. So this is the Feynman diagram I draw for this at tree level. CD bar goes to L plus nu through a W boson. But we know that the initial state is not just actually a scattering state of two free quarks, it's a D meson. It's a bound state of those two quarks. And what factorization tells us is that we can deal with these two pieces separately. So when we go to write the amplitude, we sort of write the usual perturbative pieces. You know, there's some spin piece for the leptons on the right-hand side. We have the coupling and the W boson propagator here. This will turn to G Fermi. But then we add on this extra piece here, and this extra piece that we add to the amplitude accounts for the fact that the initial state is a meson, and not just two separate quarks. And it's exactly this matrix element that's related to the decay constant, right? So in the end, the decay rate depends on just this single number, which is the decay constant. But the amplitude we define this through is the amplitude for overlap of a D meson with this operator, which we recognize as just the piece of this is exactly this vertex here. This is the coupling of the quarks inside the D to the W, basically. being a little inaccurate. Strictly, this vertex is a left-handed coupling, so this should be a left projector, but the piece that survives and gives a non-zero contribution is this gamma 5 piece. And then the final state is the vacuum, right? And that's because from the perspective of the strong dynamics, these quarks are just disappearing into nothing, right? So that's why we have the D plus the vacuum matrix element is what we put in for this diagram. Okay, so we go compute this on the lattice, we get the decay constant, and then the final amplitude can be written like so. Okay. Second thing I want to mention is scale setting. And this is sort of, again, some place where there's sometimes a disconnect with experimentalist phenomenologists. Of course, as we know, lattice is numerical calculation. It gives us dimensionless ratios. It gives us numbers. To actually interpret the numbers we get out of the lattice, we have to fix some physical scale. We're very familiar with how to do this in QCD, and there's many different ways to do it. We can use meson or baryon masses. We can use some of the more conventional lattice scales, potential scales like R0 and R1, scales defined from gradient flow. And in QCD, there's a sort of generally equivalent. You may have your own reasons for picking one of these particular scales, but they all sort of do the same job. If you're connecting to a beyond the standard model theory, you may actually be forced into using a particular scale, or there may be a particular scale which is especially convenient. Right, so the appropriate scale depends strongly on the model of interest. Like if you're matching on to a composite dark matter model, the dark matter is, say, one of your baryons, almost certainly that's the particle you want to use to do scale setting, because that's kind of a natural scale that you're most interested in. Okay. And in terms of presentation, right, you have to be ready to present your results in terms of whatever the appropriate scale is for the BSM theory. You should beware of phenomenologists who want their results in terms of quote unquote the confinement scale, right? So lambda QCD, this is a thing that phenomenologists love to write down, but what is that scale? I've seen all kinds of definitions. Maybe this is the nucleon mass is a reasonable lambda QCD, rho mass. Some people like 4 pi f pi. So the cutoff of chiral perturbation theory as the confinement scale, lambda QCD. You could even use TC. Obviously, all of these scales are going to be pretty different from each other, right? So obviously, this is sort of a squishy concept, and if someone wants results in terms of the confinement scale, you have to clarify what they actually mean. It's better to set the scale in terms of something that's actually physical. The other thing I'll mention very briefly is the perturbative lambda. So sometimes when someone coming from continuum physics talks about the scale of the theory or the lambda scale, they mean the perturbative lambda parameter. And this is well defined, but it's really inconvenient. So one, this is RG scheme dependent. It's also a very arcane thing. Like I was going to write down the definition of the lambda parameter here, but I couldn't find one that I could understand, basically, and write on a slide. So it's defined it's defined as something that emerges from the running coupling, the beta function, but in kind of a strange and unnatural way. There are lattice calculations of this, of course. You can calculate this on the lattice. So in QCD, there are computations of the MS bar lambda parameter, but this is a really inconvenient scale to match on. So if a phenomenologist wants things in terms of that state scale, your job is to convince them otherwise. Okay. Last thing to talk about briefly is dealing with fermion mass. And again, this is sort of one of those things that's hard for us to adjust and easy for someone doing pen and paper calculations to adjust. Right? If you're just writing down a theory, you're writing down a Lagrangian, you're predicting things on pen and paper. The fermion mass is just a free parameter in the Lagrangian, and you can just adjust it easily. When we do a lattice study, we have to fix it at the start of the simulation. It's one of the input parameters. Is the bare fermion mass. Okay, and what this means is that if you do a single sort of set of results, like you're simulating lattice QCD just at the physical point, that's great if you're interested in QCD, but they're sort of very narrowly useful because you can't easily change the fermion mass. You can't easily take that and say, well, what if we lived in a world where pions were, one GeV instead? The good news is that, in years past, we actually, there are many lattice QCD results that were sort of forced to exist at heavy pion mass, unphysical heavy pion mass, and those are now actually useful. Potentially in sort of theories that are interested in having heavier fermion masses, but still being based on SU3 gauge group like QCD. Okay. I mentioned that in passing. The other thing to be aware of is that, again, if you're working in the continuum, the quark mass is a great free parameter, just something you write in the Lagrangian. For us, they're inconvenient because the quark mass gets renormalized. Again, the quark mass itself is something you have to define in a scheme. It's not RG invariant. And it's generally better to use some kind of physical proxy for the quark mass. So what do I mean by proxy? So we can use the GMOR relation, which you will recognize when I write it, even if you don't recognize the acronym, just the tree level prediction of the pion mass. So m pi squared is some constant times the quark mass. And this means instead of using the quark mass, we can trade it for m pi squared. And m pi squared doesn't renormalize. This is just some physical scale, right? People often do this in lattice QCD in practice. You can identify how heavy the quarks are in the lattice simulation by asking how heavy the pions are. This is good. This is RG independent. There's no scheme dependence to worry about. It's still dimensionful. Oftentimes we want to go a step further and compute dimensionless ratios. So for example, a dimensionless ratio you could use as a proxy for the quark mass would be, say, m pi squared over m rho squared. And this is still proportional to m at small mass. Small mass. It does have the disadvantage that it's going to saturate at large fermion mass. So as the quark mass goes to infinity, this eventually saturates and stops being a good proxy. But at small mass, it's pretty useful. So I'll show you some plots here. And all this sort of thing, stuff I'm talking about here is kind of collected in this paper that I wrote with Tom DeGrand. So these are results collected from many lattice QCD simulations across a wide range of fermion masses, but this is all QCD. And then the stars are just points taken from the PDG. And what you can see is that, if I look at, these are vector and axial vector hadron masses, and if I sort of look at it as a function of this proxy for the quark mass, m pi, this is m pi squared over m rho squared, I get a reasonably smooth curve and basically linear dependence, as I would expect, as long as I'm at a fairly sort of, as long as I don't go too heavy in the quark mass. You can see this effect that, of course, this plot ends at 1. And so as I start to approach the right-hand side of the plot, these curves curve up as this is sort of approaching saturation and no longer just being linear in the quark mass. The heavy mass, we can just switch to the quark mass essentially, and this is renormalized. But if we don't worry too much about the details of that, we can still see the sort of leading linear dependence and get reasonably close to extrapolating to these the charm equivalents of the vector and axial vector mass. Okay. Okay, good. I think that's all I want to say about this. I think we can stop the recording maybe, and then I'll answer any questions about this, and then I'll go to the questions that I